Today I'll start with the thermodynamics of open systems. We'll go all the way to adiabatic systems, adiabatic compressors. Then I'll do some 3 tutorial questions. I'll walk you through them. I'll get you guys to do it. And then tomorrow I'll try to finish the open system topic, and then move on to compressor, basically giving you tutorials on compressor design, because the lectures are not that informative on compressor design, but the tutorials are quite good. So we'll work through them. There's ideal gas laws, and there's actually other EOSs like Penn Robinson and SRK, which you can use in your design if you have a compressor. So what are we going to learn in this topic? Firstly, we're going to learn about the application of the first law of thermodynamics to open systems. So you can define what the first law of thermodynamics is and how it applies to open systems. Explain the operation of an isothermal compressors where there is no clearance volume, and you learn what the clearance volume is. You can differentiate between volume work, shaft work, and fluid work, and how that combines to give you the work within a compressor and the energy requirements. So you can calculate the energy requirements, you can calculate cost, you have your full capex. And basically how to sketch the isothermal reciprocating compressor cycle on a diagram, so the PEB diagrams, link the individual work terms, how they relate to each other, and identify how that can be shown graphically, positive, negative work and direction. We are going to talk about steady flow of energy equation, so how this affects compressors, drive and explain this steady and unsteady flow, differentiate between steady and unsteady flow, and we're also going to prove the adiabatic process, so drive the equation again, but it's very similar to closed systems, so you covered that last week in that workshop style. So the math is exactly the same, it's quite straightforward. To start with reciprocating compressors. These are usually ideal for low mass flow gases and high pressure ratios. So you're starting with a low pressure, you're compressing to a high pressure, but your flow is quite low. They're quite cheap, they're quite very, very, very regularly used in the gas industry, LNG, pumping, things like that on ships. They have low displacements, so they're quite bulky, they're very expensive, and sorry, that's actually wrong. So this actually applies to a rotodynamic compressor, my bad, put it the wrong way, and they're quite bulky, they're quite expensive, but they can move quite a lot of gas at any stage. So this is rotodynamic compressor, so ignore that line and I'll come back to it. With reciprocating compressors, they're quite slow. They're air cooled or water cooled, so they're usually considered polytropic. Yeah. So at any stage, volume, temperature changing. Again, if we go back to the previous one, so that applies to, so a low displacement, bulky and expensive applies to rotodynamic compressors. So high mass flow of gas, high pressure ratio. And these rotodynamic compressors can operate very high speed, and they're almost adiabatic. So it follows your adiabatic rules. You can, and you pretty much assume always it's adiabatic. Let's talk about the reciprocating compressors, how they operate. So imagine the piston moves. So the piston moves down. This is not the best drawing, but this piston moves down. As it moves down, it creates a vacuum or a pressure differential. So as soon as it moves down, your inlet valve opens up. Just imagine your inlet valve opening up, so it lets the gas in. And as it lets the gas in, it continues moving down. This is your mechanical work. And when it gets to the bottom, your inlet valve closes. When it pushes up, you compress, but your outlet valve and inlet valve are completely closed. So imagine there's something on top of your outlet valve, and your inlet valve is closed due to pressure. And it moves up, it compresses to the point that the pressure inside your valve, inside your piston, is above the threshold pressure of your outlet valve. So it opens up, and it lets your gas out. So you get the gas at pressure 1, let's say 1 bar. It pushes it up to, let's say, 3 bar, and it opens up the outlet valve, and that's basically your compression cycle in the reciprocating valve. So the reciprocating piston, so it continuously moves up. It's like an engine, basically. So piston closes, the outlet valve at outlet pressure opens and pumps your gas out. So we are going to consider there's no trapped gas, so there is no top cycle. Yeah. So when the piston goes all the way up, you assume it goes all the way to the valve. There is no, in real life situations, there's some space where it doesn't hit the top of your piston, doesn't damage it. But in this case, because we're considering ideality, we just think it goes all the way up. Think of it like a syringe, you push it all the way up. Yeah. So that means that no gas is trapped within the piston, and hence the inlet valve will open immediately as the piston moves down. So if there is no gas, as soon as you move down, the inlet valve opens. But in reality, the piston moves down, it creates a differential pressure, and it opens up. The difference between our ideal situation and reality. As soon as it moves down, it opens in our case. So B opens, piston down. So the swept volume is the volume swept out of the piston from the top dead center. So the top area is always called the top dead center. In this case, it's 0. So it starts. Imagine your syringe is all the way at the top, and you move it down. That's your top dead center. And when you get all the way to the bottom, that's your bottom dead center. And so from the top dead center all the way to bottom dead center. And the top dead center, as I explained, is basically the top of your piston, and the bottom is the farthest point your cylinder, your piston moves within that cylinder. Yeah. So going over it again in a slightly more graphical way. So at stage 1, your inlet stroke. The piston starts at the top dead center. So this is point A on your graph. So this is your initial pressure. As you move down to point B, which is your bottom dead center. So this is that differential pressure. The pressure inside the cylinder is the same as the pressure outside. Yeah. So valve is open, no compression yet. The inlet valve is open and the outlet valve is closed at this point, so the entire stroke. So your P1 equals P inlet. Your P1 equals the pressure of your inlet equals the pressure of either atmospheric pressure or your inlet line. So you can have series of compressors, you can have compressors in parallel, so your inlet can be from another compressor. Remember, it's not always going to be 1 atmosphere. It could be anything. So pay attention to everything. So at stage 2, the piston moves from B, which is your bottom dead center, to C. So this is when both valves are closed. So it moves up. It compresses. So imagine you have a syringe. You put some paraffin in it at the top. So when you push, there is quite a lot of resistance, and you're compressing that gas above the initial pressure. So you're going to P2. This is your compression stage. So V in and V out are closed. Your P1 is going towards P2, and your P2 is bigger than P1 because you're compressing. Same as volume. Your V2 is smaller than V1 because, again, you're compressing. Stage 3 is your exhaust. So this is basically your outlet pressure. This is the pressure you want to achieve using that single compressor. So your piston moves from C to D in this case. So imagine your piston is at its highest pressure, your outlet valve is about to open, and this is at the top dead center in our case. So it's pretty much, we assume there is no space, so it goes all the way up and your outlet valve opens. The gas you have at your outlet is the pressure you want. So your V in closes, your V inlet is closed, and your V outlet is open. Hence, your P2 equals your P outlet in this case. Now, this is your new pressure, and the P outlet is basically the pressure you wanted. Remember, so you have your P inlet, and now you have your P outlet. And V2 equals 0 because we assume there is no dead volume. So your piston goes all the way to the top. So let's talk about single stage reciprocating compressors. Fun stuff. So these are usually polytropic, so cooling is not enough, so because they're cooled by air or water at any stage, so you cannot constantly cool it to compensate for the PEB change. So they're not. It's always going to be polytropic, but majority of times you don't consider it to be polytropic in this course. Just so you know, they're mostly polytropic, and you will see that in fourth year energy generation and utilization. You will definitely use this, and it'll come in useful. Anyway, 2 years from now. So at the isothermal stage, you're doing minimum amount of work. So isothermal, minimum work. Remember that. For polytropic, your polytropic work is bigger than your isothermal work, but still not as large as when you have an adiabatic system. So this is the largest amount of work because you have no heat input or heat dissipation at any stage. Best insulation in the world, remember that. That's adiabatic. Just a note, rotodynamic compressors usually operate adiabatically because they move so quickly, and single-stage reciprocating compressors usually operate polystropically because of the low speed. That's kind of thing that might come up in the exam. I haven't made your questions yet. I'll be making them this week. So, isothermal compression with no clearance volume. So this is volume work, and this is in line with volume work and shaft work. There are usually 3 stages. The work is your compression, and it's the movement of your gas. So that's your work. You're compressing the gas, that's the work done, and how much you move this gas. You've seen all of this before, so shouldn't be too bad. Your volume work between 1 and 2, so statement from piston movement from 1 and 2 is V2 over V1 PdV, negative, because it's work done. Yeah. Now you can apply this to each stage of your compression. So remember there's 3 stages: piston moving down, A to B, B to C compression, C to D exhaust. So you have 3 stages of work. You have volume work, you have fluid 1 work, fluid 2 work, and we'll cover that in a second. So from B, bottom dead center to C. So first stage is top dead center to bottom dead center. From B to C is bottom dead center to C. Volume work is compression. So this is basically volume change, right? VC over PdV in relation to VC VB. And volume work in this case equals nRT log of P2 over P1. Everyone's seen that? Everyone happy with that? Yeah? At this stage? I'll let you take notes. So the work in this case, the work is positive because you're doing work on the gas at in stage BC, at stage B, C, right? Because you're compressing, positive volume work. This is the work needed to compress the gas, but not move in or out, the in or out outlet. So the valve in or out are completely closed at this stage. Third stage is your isobaric exhaust stage. Your volume work, the volume work required to open the valve out equals VD, PdV in relation to VCVD. So again, your first stage is the same, second stage is volume work, third stage is pressure change. Yeah, so volume work out equals P2 VD minus VC, because your pressure is constant. So pressure changes stage B to C because you're compressing, and there is no and pressure doesn't change from C to D because there's no pressure relief. It's exhaust, but it's not going into atmosphere. It's staying at that specific pressure. So 3 bar, you want the gas at 3 bar, so the exhaust is at 3 bar. It's in the, think of it, it's in the pipe, yeah? And hence, volume work out equals P2 VC because there is no volume work, there is no VD. VD equals 0 because top dead center. We assume there is no dead volume. Again, this is positive work because you're doing work on the gas. So positive, and when you're expanding, that's negative. So AB. All right, strange. Let's talk about the network required for reciprocating compressor. So the network, as I mentioned, is the total work requires the volume work in, compressor moving down, the piston moving down, the piston plus the volume work of compression, so piston moving up to, all the way to the top, and then the valves opening, volume work out. Yeah. If you substitute the previous equation, so AB is negative P1 V1, so your initial pressure volume, plus nRT log of P2 over P1, so this is your volume change, plus P2 V2, again, exhaust. And you consider VB, the volume at B equals V1, right? So this is your initial volume. You have your dead volume, piston moves to bottom dead center, that's your VB, V1. And VC is your V2 all the way up. So you have 2 volumes, remember. This is just the gas before exhaust. Hence, and also the fluid work is, fluid work 1 is negative P1 V1, so the first time the work is done on the fluid. And fluid work 2 is when it's exhaust, at the exhaust stage. So it's P2 V2, yeah? So the cross-hatch areas cancel out in this case, right? And the network input is the hatched area to the left, and the network input is volume work P2, P1, VDP, so the change in volume with respect to pressure. Yeah, this is just the shaft work, so the movement in the shaft, yeah? So let's start with the network again. We know that the total work equals the volume work N plus the volume work of compression plus the volume work of the output. Hence, V work plus the fluid work 1 plus fluid work 2 is the total work of the system. And your, in this case, the volume work is your compression. Volume, this is the work of the fluid work in, and the VF2 is the fluid work out. Hence, the total work equals volume work plus fluid work. Remember, fluid work, total fluid work, F1 plus F2. Yeah. And don't worry if you're not fully following this. We'll go over it in the tutorial so you can understand a little better. So the fluid work again, as I mentioned. Let's start with that again. This is the total amount of energy required to operate the compressor, right? Where VF equals volume work fluid 1 plus fluid 2. Everyone's following that, I think. So your total shaft work is volume work plus fluid work. Where shaft work is the volume, the differential of volume in relation to P2, P1. So if we try to analyze the shaft work needed to move the piston for an adiabatic process, the P2, the change in volume in relation to P2, P1. From the first topic, we know that for an ideal gas, PV gamma equals constant. So this is your ideal gas law in relation to adiabatic gases, right? Remember that. Hence, PV gamma equals P1 V1 gamma equals P2 V2 gamma. Now, we're just going to manipulate that to get your adiabatic expansion equation. It's pretty much the same as last week. So, the shaft work in relation to pressure, if you plug in for, if you basically substitute for volume, you get P1 1 over gamma V1 over P1 over gamma, change in pressure equals P1 1 over gamma V1 in relation integral P 1 over P1 over gamma in relation to P2 P1. Following that? So remember from Thursday's workshop how your power laws change. So it's P1 over gamma to cancel out the gamma on V. And then from there it's quite easy. Yeah? So bringing pressure to the numerator, you get P1 1 over gamma V1, P2 over P1 in the derivative, the integral of P negative 1 over gamma in relation to P2 P1. Integrating, you get shaft work equals P1 1 over gamma V1 1, and you take the 1 over minus 1 over gamma plus 1, which is the integral out, the denominator of the integral out, just for simplicity, P minus 1 over gamma plus 1 in relation to P2 and P1. Hence, you have your volume, your shaft work equation, which is P1 1 over gamma V1 multiplied by 1 gamma over gamma minus 1, P2 gamma minus 1 gamma minus gamma, P1 to the power gamma minus 1 over gamma, right? Following that, power, remember your power laws from Thursday, it's pretty much that, yeah? So, if we want to remove the factor, so we're just going to manipulate that equation algebraically to get it into a new form that we can use. So we took out the factor P. So remember P1 over P1 1 over gamma. We took out the factor P1 gamma minus 1 over gamma, canceling and combining in like terms and applying the ideal equation of state. We get P1 V1 gamma over gamma minus 1, P2 gamma minus 1 over gamma, P1 gamma minus over gamma minus 1 over gamma minus 1. So you took the like terms out, cancelled out. This is what you get. I'm just going to basically, I'll finish these slides, let you go through this for 5 minutes, and I'll walk around. If anyone has questions, we'll work through it. If you're not following, it's fine. Last slide, I think. For an adiabatic process, the inlet and outlet fluid work terms are different. So the shaft work equals minus gamma over gamma minus 1 nRT. So from the previous equation, P1, V1, you insert nRT. 1 minus P2 over P1 gamma minus 1 over gamma. And for volume work, it's nRT over gamma minus 1. Multiplied by 1 minus P2, P1 up to the power of gamma minus 1 over gamma. We calculated that on Thursday. Well, we wrote that on Thursday in that workshop. So the shaft work is not equal to volume work. That's an important thing to take from all of this.